My name's Shane. I work for a company called Drake Refrigeration. Drake Refrigeration is a manufacturer of chillers, specifically in like the process cooling sphere. So just like a show of hands, how many of you guys in this room are familiar with chillers? All right, we're a good company. All right, so for the guys that are already familiar with chillers, hopefully you guys can pick up a couple things, and the guys that haven't touched a chiller or smelled a chiller, hopefully you learned something today. So, all right. Just a quick little agenda of what we're going to be going through today. We'll just do kind of a crash course on some chiller basics. We're going to kind of walk you through some chiller designs, and then we'll talk about where these chillers are being used at. So, all right. Just a little bit about me. My name's Shane. I've been an engineer at Drake Refrigeration for about 9 years now. As I mentioned, Drake's a leading manufacturer of custom chillers. Anything from like a quarter ton up to about 200 ton unit. Air cooled, water cooled, split systems, you name it, we got it. We have a catalog, but if you work with companies like Lincoln Associates, they tend to go to the secret pages of our catalog. So we get ourselves into a lot of trouble sometimes, but we learn a lot from the process. So Drake's located in Bensalem, PA, kind of north of Philadelphia. That being said, I also wanted to let you guys know that I am a die-hard Philadelphia Eagles fan. Just wanted to take this time to remind you guys that we did win the Super Bowl, and we're hoping to repeat.
Philly now.
Yes, sir. Hungry dogs.
Yeah.
I'm also a new father, too. So we just welcomed our baby boy, Henry. He came in November, and it's been fun. Challenging and fun. And if I start to ramble on and not make any sense, you can blame that on my sleep deprivation. So, all right. Let's kind of get into the meat and potatoes of this presentation. So we'll just start off with some chiller basics here. You gave me a laser pointer, I lost it. Oh, here it is. Alrighty, so this is kind of just your basic refrigeration circuit on a chiller. So a chiller is just like any sort of air conditioning unit or refrigerator. It uses the same types of components that you would see on any one of those like AC or refrigerators at your home. So we'll kind of go highlight the big stuff here. So on any refrigeration circuit, you're going to have an evaporator. It's kind of like your cooling medium between what you're trying to chill. So for chillers, we cool fluids. We don't cool spaces. We don't cool air. We're cooling either like a water, glycol solution, in some cases rocket fuel, depending on who we're working with. So essentially, you'll have a hot fluid coming in. So this could be water. You have water coming in at say 60 degrees or so. It's going to the refrigeration circuit's going to absorb all that heat from the water. The water's going to leave the evaporator cooler, hence being chilled. So what's going on in the refrigeration circuit though? There's a couple of things to kind of note here. So everything in blue kind of represents low pressure, low temperatures, and everything in red represents high pressure, high temperatures. So obviously you can see here, like we're coming into the evaporator as kind of like a liquid vapor mix. It's coming in as a low pressure, low temperature liquid vapor refrigerant. As it leaves our evaporator, that refrigerant's going to boil off from absorbing heat from the water circuit or glycol circuit. And that refrigerant's going to boil off into like a full gas. So we'll call that superheat. And it's important that it boils off into a full gas because as it travels out of the evaporator and into our compressor, these compressors cannot compress liquid refrigerant. So we've got to ensure we have superheat coming out of our evaporator. Otherwise, it's going to be bye-bye compressor. So your compressor, we're not very creative with the names. So in our industry, the compressor's going to take that low-pressure gas and it's going to compress it. So it's going to take that low-pressure gas and essentially be the driving force, and it's what allows the refrigerant to flow through this whole circuit. So as the refrigerant gets compressed, the compressor's adding additional heat to the refrigerant, as well as all the heat that we absorb from the water circuit, and it's going to travel into our condenser coil. So there's different types of condensers that you can use. In this example here, we just have like an air-cooled condenser, just like a fin-in tube sort of thing, with a fan. Fan's taking ambient air, blowing it across the coil. Air's picking up the heat from that refrigeration circuit, and it's going to convert that high-pressure gas into a high-pressure liquid. We call that subcooling. So when you get subcooling, it goes through latent heat of vaporization. Fancy term there, and it essentially means that you're taking the heat out of the refrigerant and you're getting it ready to go back into your evaporator. So now we're leaving our condenser coil as a subcooled liquid. It's traveling through our liquid line, and it's going to go into our metering device. So this metering device is the smallest component on this whole system, but it's the most important because it's what's ensuring the gas leaving the evaporator is going to be a vape. So if you're getting liquid out of your evaporator, the metering device is going to restrict itself and allow less refrigerant to flow through so you boil off that excess liquid. All right. All right. What does the chiller do? So we've kind of already talked about that, but the chillers they're a critical process in process cooling. Not really known for their sex appeal. Kind of ugly looking. They're usually hidden behind the scenes. People will put them up on a rooftop, in a mechanical room, in the back of a warehouse. We did change our color scheme to a nice gray color, so hopefully we can kind of improve our sex appeal, so to speak. Without a chiller, like most operations are going to be dead in the water. If you don't have cooling, you can't run the machinery. I have a little graphic down below. This is what a chiller would look like in like a brewery, either large scale or small scale. So all breweries are set up the same way. They got fermentation vessels, they got bright tanks, which are essentially like storage tanks for the beer. You can probably drink right out of the bright tank if you wanted to. You got different types of like air handler coils in a brewery. So if you have like a cold room, you want to store your kegs or your cans of beer, you can certainly do that. And then you also have a two-stage heat exchanger. We call that a two-pass heat exchanger. So we'll actually use city water on one side, glycol on the other side. Essentially what it does is when they're putting all the hops into this boiling water, they need to get it down to fermentation temperature. So they'll bring in 200-degree wort. We'll chill it with city water and the chiller, glycol circuit, and we'll knock it down from like 200 degrees down to about 70 degrees. And then they'll dump that right into the fermentation vessels, ferment it for a couple days, and then they'll get ready to crash it down to serving temperatures. I like my beer at like 32, 34 degrees. So you can kind of see, like, if they didn't have a chiller, they're either buying a bunch of ice or they're not making beer. So, and chillers are also designed to run year round. Like any process, any manufacturing plant, they're not just running through the summertime, they're gonna have to run year round. You can't run an air conditioner year round, but a chiller has to be designed to run year round. So you can kind of see this unit out here. I think this was Minnesota, one of the jobs that we did. There's snow all over the place, but this thing's still running 24/7. So there's a lot of different things you can do to kind of facilitate that design, just to kind of keep this unit running year round. You can imagine when it's negative 20 degrees outside, you've got that cold air blowing across your condenser coil, your head pressure in your refrigeration circuit is going to tank. So there's different things you can do to kind of mitigate that, keep your head pressures up, and we'll get into that. All right, and I promise this is the most math we're going to do this morning. I know it's 9 o'clock, so. All right, so we had the customer call in, and they say they need a chiller. The first thing we need to figure out is, well, what's the heat load for the chiller? And then once you figure out the heat load, you can figure out what size chiller you're going to need. So the way we kind of go about quantifying load in the most simplest form, we get a entering fluid temperature, a leaving fluid temperature, which is your temperature differential. We'll multiply that by flow rate. We do things in gallons per minute because we're Americans. And then we'll multiply what's called a fluid factor. So a fluid factor kind of takes into the properties of the fluid. It's one of the questions we kind of ask right out of the gate. Well, what fluid are you using? Because that's going to change our fluid factor. So I have a small example down below here of calculating fluid factor for water. So if you had to calculate the fluid factor, you're going to need to get the specific heat of the fluid, the density of the fluid, and then you multiply that by a time factor at the end here. So for water, you're going to have a specific heat of 1. So it's 1 BTU per pound degree. What the hell does that mean? So essentially it's saying that if you had 1 pound of water, it would take 1 BTU to raise it or cool it 1 degree. And then the density of water under most circumstances is about 8.33 pounds per gallon. You multiply all that stuff together to get a fluid factor of about 500. Now, if you were to add glycol to your system, like if you had to run it below freezing temperatures of water, you're obviously going to be adding some sort of antifreeze. So as you do that, you kind of derate your specific heat, and you end up with a smaller fluid factor. So let's say I had like a 30% propylene glycol mix. This number might work out to like 470, 480 or so. And you can kind of see when we punch that back into our main equation up top, it's going to decrease your heat load. All right, so I got a small example here So let's just say a customer's looking for a chiller that will cool water. They got an entering fluid temperature coming into the chiller of 70 degrees. They want to leave the chiller at 60 degrees, and they have a flow rate of 50 GPM. So that's enough information for us to quantify a load. So what we'll do is we'll just take that temperature differential, 70 minus 60, multiply that by our flow rate, and then we multiply that by our fluid factor. And we're left with 250,000 BTUs per hour, or 21 tons if you're a tons guy with BTUs. So 1 ton is equivalent to 12,000 BTUs per hour. But you can kind of see how this equation works because all the units are going to kind of cancel out. It's kind of how we do like I call it a sanity check. So you'll have temperature times a gallons per minute times the BTUs per pound per rep times pounds per gallon times minutes per hour. If you're good at math, I'm day to day, I'm good at math, but your temperature is going to drop out because that's getting divided out by your temperature from your specific heat. Your gallons per minute is going to cancel out with your density. And then your time factor is going to be canceled out by your minutes and the GPM, and you're left with BTUs per hour. Alrighty. So that's one way to quantify heat load. I wish it was always that easy, but it's not. Sometimes customers will call in and say, hey, I have a 100-gallon tank I'm trying to drop from 100 degrees to say 90 degrees in an hour. Is that enough information to size a chiller? And I'll say, sure. Doesn't really tie into this equation at all, but what you can use is the specific heat of the fluid. So if I know it's a tank of water, I know it's going to take 1 BTU to drop that tank 1 degree. So that's enough information to quantify a heat load. So if they're coming in if they're starting at 100 degrees and they want to get to 90 degrees, I got to move that fluid 10 degrees. And then I know that it's water too. So if they say it's a 100-gallon tank, I know that's going to be about 833 pounds, roughly. So it's going to take about 833 BTUs to move that tank 1 degree, essentially is what that means. But they want to move it 10 degrees, so we'll just multiply that by 10. It's about 8,300 BTUs. And if they say they want to do it in an hour, well, I need a chiller that can do 8,300 BTUs per hour. If they wanted to do it in a half hour, I got to multiply that value by 2. And if they want to do it 2 hours, I can divide that number by 2. Is that making sense? Again, this is the most math we're going to do today, so the rest is just going to be some fancy pictures. So that's definitely one way. And then the other way we kind of get requests in is sometimes contractors or Lincoln Associates will take a picture of a data tag of a unit that's 20 years old. What's going on here? Let's say, quote me chiller, and just send me a picture of an old unit. I'm like, okay. So I do some online research, figure out what that chiller is, figure out what compressor they're using, what refrigerants they were using, what temperatures they're trying to operate the unit at. Generally, that's enough information to figure out a Drake equivalent chiller for us. All right. All right, so now we'll kind of talk about like what goes into our component selection. So again, just highlighting the 4 major components here. You got your compressor, the condenser, your metering device, and your evaporator. We'll start with the evaporator. So again, just a recap from our previous slides. So your evaporator is just your cooling medium. So you're going to have water, or glycol, or rocket fuel on one side, and then cold refrigerant on the other. So the purpose of the evaporator is just to absorb the heat from the chilled fluid circuit while converting that liquid refrigerant to a gas, like your superheat. Out of our evaporator, it's going to travel into our compressor as a low pressure vaporized gas. The compressor is going to take that refrigerant and essentially circulate it through the rest of the circuit here. It's kind of like your driving force, think like a pump. So it's going to put additional heat onto the refrigerant, but also take it from that low pressure vaporized state to a high pressure vaporized state. Circulate the refrigerant through the condenser. The condenser is going to reject the heat that we absorbed from the evaporator as well as the heat added from the compressor. And it's going to convert it to a high pressure gas. It's going to convert it from a high pressure gas into a high pressure liquid. So that's your sub point right there. These expansion valves do not like to see refrigerant in its gas state. They do not work correctly. So the purpose of the condenser is just to make sure everything coming out of that condenser is going to exist as a liquid. And again, this metering device, most important component on this circuit, I would say. So it's just going to make sure that it's metering the proper amount of refrigerant to get a vapor out of the evaporator. And you can kind of see like a different visual down below. This is just the refrigeration circuit on a PT chart. So we got pressure versus enthalpy. You can think about this as temperature for convenience sake. So again, just going through the components here. So as we travel through the evaporator, we're kind of underneath this dome right here. This dome kind of represents refrigerant in a mixed state. So it's part liquid, part vapor. So as we travel through the evaporator and we leave the evaporator, we want to make sure we leave outside of the dome here. So when you're outside of the dome, especially on the right-hand side, the refrigerant exists as a gas. So as we leave the evaporator, we're picking up some superheat. So the farther you are away from this curve is how much superheat you have. So let's just say at a given pressure, at this point right here, the temperature of the refrigerant's 50 degrees. We'll call that our saturated suction temperature. It's the point where the refrigerant's about to convert to its gas phase. And then we'll physically measure the suction temperature. And let's say our suction temperature at that point was 60 degrees. So 60 minus 50, we got about 10 degrees of superheat. Life is good. All right, and the compressor's going to take that low pressure gas and it's going to compress it. So you can kind of see the bill of your pressure here. And again, the compressor's adding more heat to the system, so it makes sense for you to get farther away from the curve because you're adding additional superheat while pressurizing the refrigerant. So it's going to exit our compressor. It's going to go into our condenser coil. You can kind of see it's going through that phase change as it goes through the dome. So it comes in as a high pressure gas, enters the condenser. It starts to change its phase a little bit. Now it's a liquid vapor mix. We get to this point right here. We're getting ready to convert into a full liquid. As we exit the condenser, now we're subcooled. So kind of the opposite of superheating. It's how many degrees you are a liquid. Out of our condenser, we go back into our metering device. Another term for it is expansion. So like you can kind of tell like everything's kind of like inverse of one another. So like your compressor is going to compress the refrigerant, build its pressure. Your metering device is going to expand the refrigerant and drop its pressure. In refrigeration, temperature and pressure have a direct relationship with one another. So if you can control the pressure of the refrigerant, you can essentially control the temperature of the refrigerant. So as we go through our metering device, the refrigerant's going to drop its pressure. It's going to convert it back into that liquid vapor mix. And then we're going right back to the evaporator again. So pretty simple circuit. I think I got a B- in thermodynamics, but I know enough to kind of explain. All right. And we'll kind of do like a step-by-step for each component here. So just starting with our compressor, kind of what goes into that. So let's say we calculated our heat load from the information that the customer gave us. Now we got to pick the compressor. It's the first component we have to select, because all the other components kind of follow suit with the compressor in terms of like tonnage and capacity. So what do you need to know to size up the proper compressor? So we're going to need to know the maximum ambient temperature that the chiller is going to be operating in. We're going to want to know what chilled fluid supply temperature that the customer desires. We should know what power the customer has on site or available to them. And then your compressor capacity is going to be rated by your saturated suction temperature and your condensing temperature. So what does that stuff mean? If you get your maximum ambient and you get your chilled fluid supply temperature, that's enough information to figure out your condensing temperature and your saturated suction temperature. Up above here in red, our condensing temperature is going to be ambient temperature or maximum ambient temperature plus 20 degrees. This number can fluctuate anywhere from like 10 to 30 degrees, depending on how we want to go about sizing the coil. And then down below, your suction temperature, or your saturated suction temperature, is going to be your chilled fluid supply temp. Your chilled fluid supply temp is going to be your suction temperature minus 10 degrees. Again, that can also fluctuate. That can be anywhere from like 6 to 15 to 20 degrees. But these are pretty common values that we use in our industry. So we have a curve here of capacity on the left-hand side. Down below we have our suction temperature, and then these lines represent different ambient temperatures. So if we're looking at this curve here, you can kind of see as you increase your suction temperature or your chilled fluid supply temperature, you're actually increasing your capacity. And then the same thing with ambient temperature. So as you drop your ambient, you're dropping your condensing temperature, so you're gaining more capacity in that sense as well. So it's all about like how far the compressor needs to compress. So if you're starting at a high temperature suction and you're going to a low temperature condensing temp, the compressor doesn't have to do a lot of work. It can yield a higher capacity for you. All right. All right. I just want to throw up a couple different compressors up here. We can kind of talk through each one. Some questions we ask after we figured out what size compressor we need, we kind of say like, hey, well, do you need any sort of redundancy? These chillers are critical. You don't want to have a compressor fail on you, then you can't really cool your process. So what I mean by redundancy is like, do you want a second compressor on that same chiller circuit if one goes down? You can service it, but you still have the luxury of having a second compressor on that same chiller that can kind of take up the mantle and keep the process going. And then if you have a modulating load to prevent the compressor short cycling, it's nice to have a compressor with capabilities to kind of decrease its cooling capacity or decrease its performance to kind of keep the compressor running as long as possible. The most stress you're going to put on a compressor is at startup, so if you can mitigate how many times that compressor's got to turn on and turn off, it'll drastically improve the life of that compressor and the life of your chiller. All right, so we got a couple different compressors on here. These are all compressors that we use at Drake. I'll kind of go through each one. So the first one on the top is just a small hermetic compressor. You see this on a lot of refrigerators at home. So hermetic is generally used for low capacity, low tonnage units. It's not serviceable, like the whole compressor is hermetically sealed, so you can't get access to the motor or anything like that. Low cost, and it's got great availability. You can buy it at any wholesaler. They generally carry a decent amount of hermetic compressors. And the same thing can be said with scrolls. Although scrolls are good for like your low to medium capacities. Also not really serviceable. They're also hermetically sealed. Low to medium cost, I would say. Great availability, stocked at wholesalers throughout the US and I'm sure overseas as well. Scrolls are good because they also have modulating capabilities. So you can either do like a variable speed scroll or you can do a digital scroll compressor. You can essentially change its cooling capacity just to kind of keep it running a little bit longer. Semi-hermetic, now we're kind of getting into the bigger stuff, so medium to high capacity. Semi-serviceable, hence the name semi-hermetic. Only part of it's hermetically sealed. I think we have a Bitzer guy here too, so I'll pick his brain later. Medium to high cost, some availability, definitely has some modulating capabilities. You can do like a step-on loading type of compressor. And then the same thing can be said with our big screw compressors. We use this for high capacity jobs. We actually did a job for Chattanooga, which isn't too far from here, for the Tennessee Valley Authority. They were making boronic ice. So nuclear power plants, if they ever have like a nuclear meltdown, this is kind of going off topic, but I wanted to talk about it. If they ever have a nuclear meltdown, what they'll do is they'll make these giant ice beds, and they'll make the ice with borons. And these ice beds just kind of sit above the reactor. And if there's ever a meltdown, we'll actually dump the boronic ice into the reactor. Borons mixed with the, borons are able to like stop fusion. I'm not a nuclear expert by any means, I just talk chillers, but it was a pretty cool job that we did, and pretty local to here. I was getting off the plane, I saw the sign for Chattanooga, and I was like, oh man, I haven't been out here in a couple of years, but maybe I'll stop in and say hello on the way back. Yeah, high capacity, fully serviceable, high cost. Obviously, as you get to the bigger tonnage compressors, your price is going to increase. They're generally built to order. They have a lot of different types of modulating capabilities. And you can equip them with what we call a subcooler and an economizer. So it's just like another heat exchanger you can boost performance with. Now generally, like Drake handles the selection of these compressors. Well, sometimes our customers or our contractors will kind of let us know what they prefer, and we'll kind of go off their guidance. But when we get a tonnage, we can generally figure out like what compressors will best serve their needs. It's also based off industry too. Like if I know that they're using it for a brewery, I can assume that we're going to want some sort of modulating capabilities. All right, so that was the compressor. Now we'll talk condensers. So condensers kind of get split between two different styles. So you can either do an air-cooled condenser where you have like a fit-in tube style heat exchanger with a fan. Fan's just taking ambient air, blowing across the coil. So that's essentially free cooling from the ambient air until our government decides that air is no longer a human right. We'll see. The downside of an air-cooled unit, it's got a large footprint. As you can kind of see, these things can take up a decent amount of space. Our largest condenser is about 30 feet long, I would say, so it's going to add to your footprint. What's nice with air-cooled designs, though, is if footprint's an issue, you can generally split the unit. So you can put the condenser up on a rooftop, and you can put all your other components, like your compressor, evaporator, metering device, you can put that in yours. But yeah, there's definitely some installation restraints. If you don't have the footprint, you kind of have to evaluate some different things. Also, with air-cooled units, they need a lot of free space. You can't really put an air-cooled condenser next to a wall because it needs to get that air. We generally recommend about like 3 feet on all sides of the condenser. Recommended for outdoor use, just because you want that ambient air. And then if you have issues, if you want to run the unit year-round in the cold winter months, there's definitely some head pressure controls available, which we'll talk about, just to kind of boost your head pressure in the wintertime. And then on the right-hand side here, we got an example of a water-cooled unit. So obviously, for a water-cooled unit, we're using an external water source to cool the refrigerant. So yeah, it requires an external water source, and a lot of people don't have that. That could be in the form of like a water tower, or maybe they're pulling water out of a river if they're next to a river. City water, if you want your water bill to be wicked high. Or if you wanted to get an air-cooled chiller, I've seen people use air-cooled chillers to supply chilled water to a water-cooled unit. Seems redundant, but I guess it works. What's nice about the water-cooled is it's a compact footprint. The condenser barrels don't take up a lot of space. So you're going to have fewer installation restraints. Generally recommended for indoor use, especially if you're running water through this condenser pool. You don't really want to have that outside, especially in the wintertime. It can freeze up and destroy your system. But we have head pressure controls available for that system as well, especially if your water from the ground gets cold in the wintertime. So let's talk about that. So we'll just start off with some of these head pressure controls for an air-cooled unit. The simplest form of maintaining head pressure is a fan cycling switch. So it's just a switch you'd mount to the compressor discharge line, and it would essentially turn the fans on and off based off of the discharge pressure and keep your head pressure up. Low cost, you can pick them up anywhere. They're good for ambient temperatures down to about 60 degrees Fahrenheit. You do run into a high risk of excessive fan cycling, so it's important you set these things up. You don't want to kind of just set it up once, especially if you start the unit up in the summertime. And set it up for the summertime operation, then I'm going back out there in the spring and winter to make sure our fans aren't kicking on and off like crazy, because you'll destroy your fan motors. Some other options for the fans, we can do an electronically controlled fan, call that an EC fan. Again, low cost. That's good for ambient temperatures as low as 10 degrees. So essentially what we're doing is modulating the fan speed, changing your RPMs, changing your CFMs, delivering like a slower flow rate of air across the coil. Good.
What horsepower limitations are those EC fans?
We use 1 horsepower on our standard units, but
You don't go much bigger than that though, do you?
the example I had on the previous slide, they're about 3 horsepower.
Excellent.
So, yep. I'm sure they make all different kinds, but from what
They're pretty much limited to smaller motors.
yeah, I would say. So, I mean, if you wanted to use a bigger fan motor, you can get away with using a smaller condenser, obviously, because you can increase your CFMs and decrease the size of the coil that you would need. But the condenser I had on the previous example, that's made from another manufacturer, so we kind of work with what they got. But we have done jobs where I had to put a chiller on the back of the truck. I think it was for the University of Oklahoma. They're actually chasing tornadoes. So they needed a lot of capacity, but they didn't have a lot of space because the thing had to fit on a flatbed truck. So we ended up getting like a 10 horsepower fan motor with a smaller condenser coil. That thing was loud as hell, but it did the job. He threw a variable fan speed or variable frequency drive in the motor just to modulate it, depending on the ambient air. But yeah, it's pretty cool. We actually like parked the truck right by the tornado, just like that movie. What's that movie called? Twisted. Yeah. Big Twisted. All right. So that's fan controls. And then if you need to run it in ambient temperatures lower than 10 degrees, we also offer flooded head pressure controls. So that's good down to about negative 40 degree ambient. That is going to come with a high cost, just due to the additional components you're going to need. You're going to have to add a big receiver vessel to store this refrigerant. You also have to account for the refrigerant charge that you're gonna have to add to the system. Generally, when you add a receiver onto a chiller, your charge is gonna almost double. And refrigerant these days, as you guys probably know, is very expensive. Some other things with the head pressure controls, they need to be set up in the field generally and check for proper operation in the summer and the winter time. Down below is just an example of a flooded head pressure valve I had put into a refrigeration system. So we can kind of talk about how this works. So your head pressure valve, in this case, it's got 3 ports. It's got one port from the discharge line coming off the compressor, if you wanted to bypass the condenser coil when it's really cold outside. And then we have our condensing port right here, which will actually restrict itself to kind of, I call it stacking liquid. It essentially decreases the surface area of that coil in the winter time, and builds head pressure ultimately. So out of our receiver port, it goes into our receiver. So essentially what we're doing here is we're just maintaining the desired pressure on this line. And if we can get pressure here, we're going to stack up pressure through the condenser, and we're going to get a decent head pressure right here. So why do we have this stuff? So if you don't have any sort of means of controlling your discharge pressure, your refrigerant's not going to flow properly through the refrigeration circuit. So if you can keep your head pressure up, we use medium pressure refrigerant, so ideally we like to keep our pressure at like 250, right about here, right under our transducer. If you can maintain 250 year round, the system's not going to give you any problems. And as far as some mitigation on a water cooled condensing unit, there's definitely some options that we can pursue. So for, again, chillers operating year round, your condensing water is not always going to be 70, 80, 90 degrees. So if your water starts to come into the condenser at 50 degrees, it's going to drop your discharge pressure. So there's some mitigations we need to put in place to keep our head pressure up. So Drake generally uses what's called a water regulating valve. It's essentially like a one-pass valve. It has a small probe on the bottom here that we can mount to the discharge line. You can kind of see it in that graphic here. Just monitoring discharge pressure. It's a spring-loaded valve. So if your water starts to come in really cold, this valve will actually restrict itself, allow less water to flow through, which will ultimately build up your head pressure. It's low cost, good availability, provided at most wholesalers. So that's kind of like our standard option. If we're quoting a water cooled unit, like we're just throwing this onto the quote every single time. You can also do what's called a three-way modulating valve. Essentially what you can do is bypass the condenser and meter less refrigerant through. It kind of works the same way as a water regulating valve, but it kind of diverts the fluid a little bit better. Medium to high cost, some availability, depending on what you need. And then the other option that I have up here is just a variable frequency drive for the condenser pump or condenser flow. So you have to imagine that you got water flowing through this condenser at a specified flow rate. If it gets cold in the wintertime, you might not need as much flow, so what you can do with a variable frequency drive is just slow down the speed of that flow and control like an actual discharge pressure off the compressor. Medium cost, some availability. And there's a bunch of other options out here, but these are kind of the ones I wanted to highlight just based off the fact that I've physically put them in chillers. All right. So now we'll kind of get into the metering valve. So we're down here now. So we just talked compressors, we talked condensers, now we're talking metering valves. So some questions we ask for the metering valves. Well, not really. These are mostly questions we ask ourselves. Drake generally handles the component selection for the expansion valve. So, is your load going to modulate? That's a good question to ask. What are your saturated suction temperatures that you're trying to get to? Well, we'll know that if we know the chilled fluid temperature. Maximum ambient or the condensing water temperatures, that's something we need to know as well. Again, that condensing temperature is just going to be 20 degrees plus your ambient temperature. So, that valve can come in all different shapes and sizes. First one here is just like a capillary tube. We don't really use this on our systems. You usually see these on small refrigerator units, generally low, fixed capacities. Low cost, good availability, not really serviceable, it's just essentially a copper tube. Our bread and butter is our thermostatic expansion valve. We call it TXVs. So low to high cost, you can actually adjust the capacity. There's a spring you can set in here to get a desired superheat out of the evaporator. So if my refrigerant going through my evaporator is moving too quickly, it might not be boiling off all the liquid refrigerants. And what we'll do is we'll have the contractor, the tech, go in there, make an adjustment to the spring on the TXV, essentially increase the pressure of the spring, which allows less refrigerant to flow through, which gets you more superheat ultimately. And then the electronic version of that is an electronic expansion valve. I have a little typo there, I should say EXV. But low to high cost, self-adjusting, so we have some pretty sophisticated controls where we can calculate a real-time superheat calculation. So if you know your suction pressure and your suction temp, that's enough information to calculate the superheat. Our controller will send a command to the valve to control it to a desired superheat. So we'll say, I want the superheat to be 15 degrees. If the refrigerant starts moving too fast, then our superheat decreases, that valve will self-correct itself, close itself off, increase your superheat, and vice versa. Like if you're not throttling enough refrigerant through and your superheat's too high, it'll open itself back up again. So again, some availability, semi-serviceable. All right. Now we'll talk evaporators. So, what kind of goes into an evaporator selection? So we need to know fluid to be chilled, because obviously that's your cooling medium. That can kind of tie into material compatibility. Like if I'm doing a job for an aerospace company, they want to cool rocket fuel is highly corrosive to these brazed plates, being that they're made of copper. So we'll usually recommend doing some sort of like stainless steel or even like a titanium evaporator in that case. We need to know the saturated suction temperature of the refrigerant, and we need to know what kind of temperature differential you want to cross the chilled fluid circuit. Flow rate's helpful to know as well. So if we have all that information, that's enough for us to size up an evaporator. So brazed plates are good. They're good for like our low to medium capacity jobs. It's a low to medium cost. They have a small footprint, good availability. Not really serviceable. Like if you have a failed brazed plate evaporator, you just end up replacing it. There are double walled options available if you're doing like a potable water application. So what I mean by potable water is like drinking water, like out of that fountain in the back there. Right, my laser pointer. Sorry for that mistake. Yeah, so with your brazed plates, like a potable water option, it's essentially just like a normal evaporator, but there's a thin wall in between of just like an empty space. So essentially what that means is your refrigerant doesn't, it's not possible for that brazed plate to fail and your refrigerant to mix with your water. And then the other option on the right-hand side here would be a chiller barrel. So these are good for like medium to high capacity. It's a medium to high cost. Large footprint. It's a pretty long chiller barrel generally. They're generally built to order, fairly serviceable. Like you can change out gaskets, tubes if you have a failed tube. And they're great for like high flow rate applications. So you'll see a lot of these in ice rinks. Ice rinks have like a massive flow rate, very small temperature differential.
As far as the capacity, can you know what you say low to medium or medium to high?
Yeah.
Which capacity is it?
I'll say like low to me is like a quarter ton, so we'll say like 2,500 BTUs up to like 500,000 BTUs would be your medium, and then anything above that I would consider high capacity. Yeah, so 500 to like 2 million BTUs would be high capacity. Yep. Yeah, and then just another thing with these brazed plates, they're not really good at high flow rates, so if you're going to have a massive flow rate like 500 GPMs and above, it's probably best to go with the chiller barrel, so you're going to have a massive pressure drop across that braze plate heat exchanger. All right, so just to kind of recap the refrigeration circuit, kind of already showed this graphic, but we got our compressor taking that low pressure vaporized gas, it's going to compress it into a high pressure vaporized gas. All that heat that we have from the compressor, the evaporator is going to have to get projected from our condenser, whether that's an air-cooled or a water-cooled model. The condenser is going to take that high pressure gas, convert it into a high pressure liquid. It's going to travel into our expansion valve. Expansion valve is going to expand the refrigerant, drop its pressure, drop its temperature, and then go into the evaporator. All right, so chillers just aren't refrigeration. So it's not just compressors, and condensers, and evaporators. You got to worry about like the chilled fluid circuit as well, the hydronic circuit. So with a chilled fluid circuit, some things I'd like to talk about today. So there's a couple items to note. Obviously your evaporator, that's your cooling medium, that's what's cooling your process fluid. You're going to need pumps just to circulate the fluid to and from the chiller. Like to add tanks as well. So like with an air conditioning unit, like you're going to get volume in an air conditioning unit because it has all that space to cool. You don't really have that in a chiller unless you have a tank. You got to add volume, or you're going to end up short cycling your compressor. And then a lot of the times we'll add some secondary heat exchangers as well. Just another cooling medium. So if we had this whole chilled fluid circuit just filled with like a glycol solution, and the customer ultimately wanted water, we might tack in an extra fluid-to-fluid heat exchanger that can come in all different types of shapes and sizes. But yeah, down below we'll kind of just go through this schematic here. They generally don't look this complex for us. I just wanted to get something up there to talk about. But yeah, we'll kind of go through each one here. So you're going to have your evaporator. Obviously, that's kind of where the cooling's coming from. We'll have a glycol pump in this case, just drawing from a large 300-gallon tank. It's going to send fluid into our evaporator. It's going to chill it. So maybe it's coming in at 50 degrees from the tank. It'll leave the evaporator at, we'll say, 40 degrees, go back into the tank. And that's essentially how you're kind of maintaining tank temperature. And then, again, in this example, we have a separate process loop. So we have glycol pumps pulling off the same 300-gallon tank. It's sending fluid to that secondary heat exchanger. That fluid's going to absorb heat from the other side of the heat exchanger and send it back to the tank. So essentially we have, I call this a recirculating pump. It's just recirculating the fluid from the tank to the chiller, just to keep the tank cold. And then these are glycol process pumps, just sending fluid from the same tank, going to the heat exchanger to cool a secondary process loop. And then again on the secondary process loop, we'll say this is water on this side. Maybe the customer wants to maintain 40-degree water in this tank. And if that's the case, we probably want to maintain about 30-degree glycol over here, just so we have some heat transfer there. So they'll have a separate pump pulling off the water tank at 40 degrees, or we'll say 50 degrees. Comes into the evaporator, comes into the secondary heat exchanger, and it's going to leave colder and back to the tank. So very similar to this recirculation loop, just on a water cycle. And then same thing down below. We have a set of process pumps pulling off the tank. You go into your customer's process loop, whatever that may be. So a couple of things to note here. We got some redundancy built into this type of system. So we have redundant glycol process pumps, and we got redundant water pumps. Only one of these pumps will ever run at a time. If we have any sort of failure and our flow switch stops detecting flow, it'll shut this pump off, kick this pump on, and the customer isn't any the wiser.
Is there any difference if you want to put it on the water process or level water?
Yeah, so there's certain like rules and regulations you need to adhere to. If you're going to be doing potable water, you can't run that through like a normal braze plate because it's not sanitary. So you can either do like a secondary heat exchanger setup like this, where you have glycol on one side and water on the other. If you have like 2 degrees of separation from the refrigeration circuit, this would be like a sanitary grade setup, because there's no way the water's going to mix with the refrigerant because there's too many heat exchangers. Or you can do that potable braze plate that we talked about, where you have that thin wall. It's not possible for the refrigerant to mix in with the glycol if you have a failure, because there's just like an empty space there. Yep. Well, there's a bunch of different ways you can kind of mitigate that. All right. So let's talk pumps. So when we select a pump, it's good to know what your fluid is and what the lowest temperature of that fluid is going to be. We like to know what our estimated pressure drop is across the process, and we need to know the flow rate, obviously, because that's the whole point of having a pump. I would say the pumps, like behind the compressor, like this isn't a component you want to get wrong. Like you can have a chiller that's sized for the heat load, but if you don't have the pumps to deliver the fluid to the actual process loop, what's the point? On the right-hand side here, I just have an example of a pump curve. This is a curve of water. So we got a couple different lines here, so we can kind of go through that. So on the left-hand side, this represents like a pressure drop across the pump. So this is expressed in feet ahead. You can convert that to PSI if that's easier for you. On the bottom here, we have our capacity of the pump in gallons per minute. These lines represent the horsepower limitations of the pump. So this is a 2 horsepower motor. And this is our 2 horsepower line right here. So essentially what I'm trying to say is, don't pick a pump that's going to operate more than its rated horsepower. So when we figure out a customer's pressure drop across their equipment, we kind of factor in the pressure drop from our equipment. We have a total pressure drop, which allows us to figure out what their best pump would be. So if they tell me they need a pump that does 70 GPM at, we'll say, 60 feet ahead, well, this 2 horsepower pump would be the right one to go with. Just to kind of talk about some of these curves real quick. So this is our horsepower curve. So you can kind of see as you increase your flow rate, you're going to yield a higher horsepower from that pump. The curve here sloping down represents the actual performance of the pump. So it's pressure versus gallons per minute. And then this guy sloping up through the top is just our efficiency curve. So if I'm picking a pump, I want to make sure it kind of falls in to kind of like right on the cusp of this efficiency line. That kind of gets you your best bang for your buck. I'm not going to pick a pump that does, I'm not going to pick this pump if they said I want something that does 10 GPM at 40 feet ahead, because in terms of efficiency, we couldn't be any lower. And I also don't want to pick a pump that does 100 gallons per minute at 45, 46 feet ahead. Specifically this pump, if it's going to start to operate over its horsepower limits, once that starts happening, the motor's going to overheat and you're going to have some issues with your pump and probably end up replacing it and having to call Drake and get a bigger pump or a more efficient pump. So. And just some other things to note real quick. So this is obviously a curve for water. So it's important to know what fluid it is that you're cooling. If you start to add glycol, that glycol is going to become viscous and essentially add like an internal pressure drop. And this curve is going to look a little differently with glycol. It's going to have to be corrected, so to speak, because the fluid characteristics of that pump are going to change. So you're actually going to get less flow as you add like a glycol solution or an antifreeze to this fluid with this specific pump model. All right, and then some pump options that we can ask when we're doing a quote. Are you going to require any sort of redundancy? Down below is just an example of redundancy. So if they have a pump failure, you don't want to be dead in the water if you can't deliver the flow to your process loop. So maybe you add a secondary pump just to kind of turn on if we have some sort of pump failure here. Or maybe just for like general service. Like if I put like a filter in line with these pumps, and the filter gets clogged with the one pump, well then I can kind of just valve off that pump, turn on the other pump, clean my filter, put it back into operation, and on with that. We also ask questions like, do you want your flow rate to modulate? There's certain processes out there where they don't always want 50 GPM or 100 GPM. Sometimes the flow has to modulate to work with their process a little better, specifically in breweries. And we'll kind of get into that when we start talking about some different types of industries here. But if they want to modulate the flow, we'll install a variable frequency drive for the pump motor. It can control supply pressure, supply temperature. Generally recommended not running the pump with a VFD if it's going directly through the evaporator. You don't really want to alter your flow rates going through your evaporator coil, because then you can have an adverse effect on your refrigeration circuit. If you don't have a constant heat load going into your evaporator, the superheat on your refrigeration circuit is going to be all over the place. And that metering device is not going to know what the hell to do. All right. So some different types of pumps that we see in our industry. The ones we use primarily are centrifugal style pumps. Just essentially a shafted motor with an impeller mounted onto it. Ideal for like low to high flow rates. It's good for medium pressures, medium temperatures. When I say like medium pressures, medium temperatures, I'm talking like maybe 50 PSI, anywhere from like 40 to 70 degrees per second. You can equip these pumps with VFDs if you need to modulate flow. And again, that's good for like medium pressures. So if you need something for like a higher pressure application, we generally recommend like a multi-stage centrifugal pump. Ideal for low to medium flow rates, good for high pressures and medium temperatures. Don't recommend equipping this type of pump with a VFD. If you put a VFD on this type of motor, you're not going to yield your pressure, your high pressure that you're looking for. A couple different options. So a couple other options. We got a gear pump. So a gear pump doesn't really utilize an impeller. It actually just utilizes 2 gears to push the fluid through. I don't really have a graphic here. Just take my word for it. So it's ideal for low to medium flow rates. It's good for low to high temperatures, ideal for high pressure applications. Must be equipped with a VFD. So with gear pumps, like they can overcome any pressure. So if you put a gear pump into your process and some Joe Schmo closes the bolt down the line, that pump's going to keep building pressure until something breaks. So you got to put a VFD on it and monitor pressure. Otherwise, you're going to be on cleanup duty. So we used this pump recently on a aerospace application. I actually wanted to put a chiller next to a rocket, and the chiller had to push fluid all the way up to the probe that they were launching into space, which was like 200 feet in the air. So you had a decent amount of head pressure that we had to overcome. So this gear pump was nice. They had a low flow rate application. Like all the chiller had to do was pull like the flight controls. I say only, but so yeah, it had to push up 200 feet in the air, had a low flow rate. So this was the right pump for us to use. And then down below is what I call a mag drive pump, magnetically driven. There's it has an impeller, but it's not physically attached to like a motor shaft. Just like its name, it's a magnetically driven impeller. So it's great for low temp applications, especially when your fluid temperatures get to like negative 20 degrees and below. You're going to have significant heat transfer from the impeller to your motor. When that happens, you can end up seizing up your motor because it's going to get too cold. So what we do is we implement magnetically driven impellers that never actually touches the fluid, essentially. Well, I mean, the motor doesn't actually physically touch the fluid. Ideal for, again, low temperatures, ideal for medium pressures. You can also equip this type of pump with a VFD. All right. So let's talk tanks. First question I usually ask is, well, do you need a tank? For tanks, some other questions that we ask is, do you require tight temperature control? If the answer is yes, you're getting a tank. How much volume do you need? Obviously, that's what tanks do, they add volume. And will the tank be operating under pressure? All key things we need to know. So, just off the second bullet point here, do you require tight temperature control? If yes, we're probably going to set this tank up in a recirculation system, which we'll get to on the next slide. How much volume do you need? They say 500 gallons, they're going to get a 500 gallon tank. But generally, you can kind of quantify how big of a tank you need, at least on our end. Like we can figure out, a good rule of thumb is you figure out what your largest pump is that's drawing off that tank. Let's say it's 100 ppm, and I'll multiply that by 2, and I'll say I need about a 200 gallon tank. That's kind of like a general rule of thumb in our industry. You can also size tanks to kind of prevent compressor short cycling. That kind of ties back into that specific heat we talked about on like the first couple slides there. It takes 1 BTU to cool 1 pound of water 1 degree. You can kind of quantify how often that compressor is going to have to turn on and off based off your tank size. So if I wanted the compressor to, if the compressor is going to be turning on and off quite a bit, I'm probably going to put a decent sized tank on this system, just so that when it is in an off cycle, the compressor can kind of just stay off for several minutes, maybe like 10, 20 minutes or so, before that tank heats up again and the compressor needs to fire back on, cool the tank back down. So stainless steel tanks, they're good. They can operate under pressure. They're ideal for closed loop systems. What I mean by a closed loop system is like the fluid just circulates through the process and back to the chiller. It doesn't dump anywhere or anything like that. It's just a closed loop system. Ideal for low to high temperature applications. So again, what's that mean? Negative 40 to, let's say, 100 degrees or so. Medium to high cost. Generally, these stainless steel tanks are built to order. And then the other option here is a poly tank. So it's a plastic tank. You can't pressurize a plastic tank, so that's one of the downsides. It's good for adding volume to your system for sure, but being that it's a plastic tank, don't recommend using it for anything other than like medium temperatures, which I would say is like 50 to 70 degrees or so. If the fluid gets too cold, the tank becomes brittle, it can fail. If the fluid gets too hot, the tank gets warped, it can fail. It's a low cost and good availability. You can buy them on Amazon if you want to. Alright, so there's a couple different ways we set up tanks in our chillers. I kind of already talked about this a little bit. First one's a recirculation setup. So this would be a setup if you wanted like tight temperature control. So let's kind of walk through this a little bit. So in this example, we got our chiller on the left-hand side here. We got our tank in the middle, and then we got a couple different pumps. We'll call this our recirculation pump. It's just always running. It's circulating that tank temperature through the chiller. It's coming in at say 50 degrees, leaving the chiller at 45 degrees, and it's essentially just maintaining this tank at 50 degrees. So you have kind of on-demand cooling whenever you need it. And then on the other end, we have our process pump. It's taking that fluid, that 50-degree fluid from that same tank, sending it out to the process loop, and it's going to return warmer back into the tank. But in this case, at least the customer is always going to get the desired temperature that they want. So with a recirculation tank, if everything's sized properly, you can generally get between like 1 to 2 degrees of tolerance. Yeah, so obviously some advantages of that. Kind of already talked about the tolerance there. It's a 2-pump dual loop system. It kind of isolates the process flow. So if you have any sort of like modulation in the heat load over here, our chiller's never going to see that because this tank's going to eat all that modulation. Yeah, so the evaporator's only ever going to see the recirc pump flow rate. It's a constant flow rate. If you can have a constant flow rate, constant temperature feeding this chiller, the chiller's going to be very happy because it doesn't have to make any sort of altercations to that metering device, and you're going to get a constant flow or a constant performance out of your chiller. Yeah, and the glycol tank's just going to stay cold even when the process is off. So they're just going to, whenever they want to turn on their process, they're going to have 50-degree fluid ready to go. So there's no downtime waiting for the fluid to cool down. They can run their process as soon as they come in the morning, have a cup of coffee, they're ready to rock. Obviously, some disadvantages with this type of system, it's going to add additional costs to your chiller because now you have to add an additional pump in your recirculation pump. And then with to maintain a 50-degree tank in a recirculation setup, you got to operate at a lower temperature. So even if you want 50 degrees in your tank, well, the chiller's going to have to operate a little bit lower than that just to keep the tank at 50. So when that happens, you're going to have to drop your saturated suction temperature. And if you recall from that previous curve with the compressor, if you decrease your saturation suction, or if you decrease your saturated suction temperature, you're going to decrease the compressor. You might end up having to go with a bigger chiller. So there's definitely some advantages and disadvantages, but I think the advantages kind of outweigh the disadvantages.
Shane.
Yeah.
Let's take just a couple more minutes. We got to get to the next speaker.
Oh, yeah, no problem.
If we could.
What do I got?
Sorry to cut you short.
No, you're good.
Take just like 2 or 3 minutes just to.
Yeah, no problem. All right. We don't really need to get into industries today, so we'll just wrap up components and we'll get to go. Last setup for a tank, storage tank, essentially just adding volume to the chilled process loop. So obviously some advantages, you're going to add volume. It's a single pump, so you can kind of save on your costs there. You don't need to add that secondary pump. Some disadvantages, you're not holding temperature as well with a recirculation system, or as well as you would with a recirculation system. It's not going to absorb those process variations. And the glycol doesn't stay cold when the process is off, so you're not going to have that on-demand cooling. Just talking some secondary heat exchangers on our hydronic circuit, all different styles here. So if you have a secondary cooling medium, like if you want to cool water with glycol, you do a brazed plate heat exchanger, which we kind of already talked about. There's plate heat exchangers available as well. They're really good for gas cooling, and they're fully serviceable. You can actually unbolt this plate heat exchanger, pull the whole thing out, clean each plate individually, and put it back together again. Compared to the brazed plates, you're going to have a higher cost of the plate and frame. They're generally built to order. They're good for medium to high capacities. We can also implement what's called fluid coolers. So if you were operating a unit in Minnesota, we'll say, and you didn't want to run the unit, you didn't want to run the chiller when it gets below like 10 degrees, you can get away with using a fluid cooler. It'll kind of take over for the chiller in the wintertime, essentially bringing in cold ambient air to cool the glycol circuit or the water circuit, and save the customer a lot of money in terms of like power consumption. Because at this point, it's just, the fluid cooler is just a set of fans that turn on and off to get a desired glycol temperature. And then air handlers is the other heat exchanger there. So we'll see those now in a lot of storage rooms, big warehouses. So it's essentially taking the cold glycol, running it through an air handler. Air handler takes air, pulls across the coil, cools the air, cools the room. So, I'll just pop through a couple of these industries real quick, and then I'll wrap up here. So yeah, we're big into the breweries. We love beer. We like wines too, and liquors, so we do all that. We do a lot of dairy farms. You see chillers a lot in food production. Like if they need like near freezing water to go into like their batches, we definitely can help out there. A lot of different types of medical applications, MRI machines, linear accelerators, body temp blankets. We're not huge into the comfort cooling, but if you have a chiller used to cool your house, you're probably a millionaire or a billionaire. And then, yeah, we're big into the refrigeration industry as well, so like ice rinks for like the low temps, rocket fuel, we kind of talked about that. Industrial, like a lot of different types of applications there, plastic injections, welding machines, things of that nature. All right. Yeah, we'll just wrap up on this comfort cooling. So we've been doing a job for a riverboat casino for like 15, 20 years now. I never got invited onto the boat, but this is just like a basic layout of what this would look like on the boat or maybe at a big billionaire's house. So you'll have a chiller in a remote area. It's going to take fluid from a volume source, send it through the chiller, cool it into an air handler. Air handler delivers cool air into a room. Well, yeah, we'll wrap up there. Sorry it took so long. I didn't time myself in the hotel room, but if there's any questions, I can certainly answer them. And again, I just wanted to thank Lincoln for having me out here. Thanks for setting us up, Chris, Morgan.
Ammonia.